In this video, we will revisit a demonstration that we did in class where we had pennies on the end of a ruler. Here we've got pennies on the end of a ruler, and we're going to let the ruler fall. And you'll see there that the pennies seem to hang in the air above the ruler. And what we'd like to do today is investigate why. I'm going to fast forward to a little bit better view. We've got the pennies spread out along the length of the ruler. Now what will happen?
Right.
And you can see on the right hand side, there we go. I've circled the pennies in this view. And on the right hand side, we see someone's elbow and they let go. And then you can see the pennies on the right stay on the ruler and the pennies on the left
Right.
come off. We'll watch it again. So again, the pennies are spread out along the length of the ruler. And you can see the penny on the left comes off, but the question we want to look at is where on the ruler does the penny stay on the ruler and why? So I'm going to switch over to Notability. I've got a picture of the situation, pennies and a meter stick, and I'm going to draw a force diagram. So for the ruler, I'm going to go to the center of gravity of the ruler, and I'm going to draw the weight of the ruler, which would be equal to the mass of the ruler times g. Now, while the ruler is not moving, we've got a pivot over here. It was a table in the video. And we've got somebody pressing down on the ruler. So we've actually got the table pushing up. Maybe I should make that a bit longer. So there's the table force. And then in this scenario we had, well, let's look at the instant that we let go. The instant that we let go, the very first instant that we let go, Fn is actually equal and opposite to Fg. But then the meter stick starts to accelerate. And so we're going to take a look at this in terms of torque. So we know that torque is equal to moment of inertia times angular acceleration. And we know that torque is also equal to force times distance times the sine of the angle. So I'm going to make some substitutions in this scenario, and I'm going to set them equal to each other. I'm going to say that I times alpha is equal to Fr sine theta. And that's a very, very useful substitution. Now, this meter stick is a thin rod pivoted at one end. So I is going to be 1/3 mr squared. Alpha is unknown. On the other side, the force that creates the torque is Fg. And Fg is equal to mg. The distance between the pivot and the force of gravity is half the length of the meter stick. So we'll call that 1/2 r. And then the angle between r and F here is 90 degrees. So we've got the sine of 90. Okay, so now I can do some algebra. So I can divide both sides by m. And when I do that, I get 1. What else can I divide out? I can divide out 1r. And I know that the sine of 90 is 1 as well. So I've got 1/3 r alpha equals g over 2. And now I'll solve for alpha. Alpha will equal 3g over 2r. Now, this works for any thin rod. This happened to be a meter stick, so r, or the length of it, was 1. So alpha would be 3g over 2. And if I actually calculate 3g over 2, 3 times 9.81 over 2, I get 14.7 radians per second squared. So let's think about that for a second. So this whole meter stick has the same angular acceleration of 14.7 radians per second squared. What's going to be different, though, is what's going to be different is the actual acceleration. The linear acceleration is going to be bigger at the end than it's going to be closer to the pivot because of r, because of the distance from the pivot. So if I wanted to compute the acceleration at the end of the ruler, I would take the angular acceleration times the length of the ruler, and I would get 14.7 times 1, or 14.7 meters per second squared at the end of the ruler.